So what can I tell you about the Claisen reaction? Well, it's kind of more of the same. It's just like we've seen in chapter 20 and the beginning of chapter 21. It's all up, down, out. Here is our nucleophile, attacks our electrophile, kicks up the pi electrons, they slam back down, and kick out the leaving group. Up, down, out. And speaking of patterns, doesn't really matter what the leaving group is, it just modifies the reactivity. So the acid halides are super reactive, acid anhydride also very reactive, acids and esters not so much, and amides pretty much not too reactive at all, which is a good thing since you and I are pretty much made up of amides. But moving right along, what about nucleophiles? What nucleophiles are we looking at here? Well, we've seen in chapter 20 the hard nucleophiles like the organometallics and the reducing agents. So the organometallics like the Grignard and the organolithiums add two times always to get to the tertiary alcohol, whereas a cuprate will stop and just give you the ketone. If I add water, I'm doing a hydrolysis. If I add an alcohol, I'm doing maybe a transesterification. Those can be either acid or base catalyzed, whereas these, of course, are under basic conditions. Addition of an amine gets me to the amide, etc., etc. So what's missing? Well, what's missing is the enolate. That's the nucleophile we're going to look at in the Claisen. So here we go. Here is our carboxylic acid derivative, and there's an enolate waiting to react. So, boom, up, down, out, right? Absolutely. Here's the tetrahedral intermediate, right here. And once it collapses and kicks out my leaving group, this is your Claisen product, a 1,3-dicarbonyl. There's my leaving group, and what you see in this equilibrium is that there's a powerful driving force for the Claisen, in that the hydrogens attached right here are part of an active methylene. Very acidic, low pKa, and since we're under basic conditions, that's going to be deprotonated, yes, in a heartbeat, to give you the enolate, which can be reprotonated. And bottom line is, these guys actually favor being in the enolic form. So for certain molecules that have this 1,3-dicarbonyl relationship, you can actually see that hydrogen in the proton NMR. So the driving force is the super stable intramolecular hydrogen bonding from the 1,3-dicarbonyl. Alright, so the Claisen condensation, not the Claisen rearrangement, which I hate to tell you we're not going to learn about. I'm sure you're disappointed. The Claisen condensation is officially taking the enolate of an ester and either reacting it with itself or with another ester. So we've got one starting material being both nucleophile and electrophile. Doesn't have to be an ester and an ester, although that's the strict definition of a Claisen. Really, it could be any old enolate adding to an ester as the electrophile. The bottom line, no matter what it is, you're talking 1,3-dicarbonyl, and by that I mean this relationship. There might still be a leaving group here, but these two pieces are 1,3 to one another. Now, the Claisen, like the aldol, can be crossed. So here's a nice example. If I take isopropyl benzoate, which I'm sure that nomenclature just springs to mind immediately, isopropyl benzoate and methyl propanoate, I can, under these basic conditions, deprotonate my methyl propanoate up, down, out to give me my Claisen condensation product. So there you have it. Once again, I will point out the 1, 2, 3 relationship of the two carbon-oxygen double bonds that's screaming, hey, this is a Claisen. Alright, a couple of examples here. We've got this basically a derivative of an amino acid and the enolate of a tert-butyl ester. Oops, up. Well, I won't even try to draw it out. Up, down, out. That's my electrophile, that's my nucleophile. There's the Claisen product. Next example is a promising candidate for the treatment of atherosclerosis. Look at this one carefully. This one's not quite as obvious. It's quite clear, I hope, that this is going to be where my enolate is formed, and I hope it's quite clear as well that it's going to react with this electrophile and kick out my ethoxy. But it seems to me then that that would give me this guy. Oh. Alright. And that is in fact the Claisen product. What you should do is figure out how these two react to make that. That would be a great little mechanism for you to work through. Alright, so at this stage, we've been through, as promised, weeks and weeks of carbonyl and carboxyl chemistry. Lots of nucleophiles meet electrophiles. Let's try to summarize by recognizing the patterns of the products. So here we see the familiar 1,3 relationship of a carbonyl and a hydroxyl group. So not a 1,3 relationship of two carbonyls, but one's a carbonyl, one's a hydroxyl group, and if that dehydrates, the, I hope, familiar alpha-beta unsaturated ketone. Screamin' aldol. Aldol all the way. Alright, so that's from the addition of an enolate to itself in this example, or another aldehyde or ketone. Now we see that the 1,3 relationship between two carbonyls is the Claisen. And it's worth pointing out here that oxidation states can help you out. So here's an oxidation state of +2, oxidation state of +3. So it stands to reason that you're going to have a difference in the oxidation states of your aldol and your Claisen product. So we have our aldol product giving us an oxidation state of 0 on carbon 3, whereas the oxidation state, well, actually we should point out the oxidation state over here. We went from +3 to +2. So really what I want to emphasize here is that aldol gives you a lower oxidation state because it's starting in a lower oxidation state. Claisen gives you a higher oxidation state because you're starting in a higher oxidation state. Finally, what's this bell and whistle? Yeeks, a 1,5 between two dicarbonyls. Well, I'll let you wonder about that question mark there, but remember that this is the Michael reaction. And all of these guys are examples of enolate chemistry. Okay, so I've already alluded to this, but why does this work? Why does this whole Claisen condensation thing work anyway? Well, again, it's equilibrium. All of these are reversible reactions. But when that nucleophile reacts with this electrophile and does the old up, down, out thing, the whole deal, oops, well, that's all right. The whole deal is that this guy, under basic conditions, is going to be way, way, way to the product side in terms of acid-base chemistry, because this is a very stable carbanion, as you know, because it can be delocalized by resonance. So the driving force is acid-base chemistry, and as I saw earlier, the stability of the product of the Claisen reaction is from the intramolecular hydrogen bonding of the 1,3-diketone. So that's what drives the formation of the Claisen product, the favorable deprotonation of the active methylene. Now, just like aldols and the Robinson annulation, sometimes Claisens can be intramolecular. So let's look at this problem in a little detail. We have an ester and an alpha-beta unsaturated ketone. We're under basic conditions. What's going to happen? Well, what's going to happen for sure is that I'm either going to make an enolate there or an enolate there. I don't know which way. I don't know what's going to happen. So let's start with this one and see what happens here. If I do that, I'll get to this guy. I'll kick it up, down, out. No, we're not up, down, outing. We don't have a... Oh, yeah, we do have it. Whoa, whoa, whoa. Let's get this back to... What we're doing here is we are doing up, down, out. So that would give me... CH2, CO, CH3. Okay. So there's my Claisen product. Looks fine. All right. What happens if I do my enolate on the ester? So if I enolize over here, does that get me any further, if you will? All right, well, this is an example of a Michael. Remember that the enolate is a soft nucleophile, and the beta carbon here is my soft electrophile. So addition of the enolate there takes me to this place, CH2, CH. Oh boy, you really, really want to draw everything out when you're doing these Michael reactions. So there's that intermediate, and that intermediate is just going to get protonated by my alcohol. So the product of this particular step is my 1,5 dicarbonyl, 1, 2, 3, 4, 5. But I'm still under basic conditions. Aha! So both pathways gave me a stable product, but only this one can take us to an even more stable product from intramolecular cyclization. If I form my enolate here, That doesn't do me much good because the only electrophile it can react with is right there. That's a four-membered ring and definitely not favorable. Okay, but if I form my enolate here, I think 1, 2, 3, 4, 5, 6. Wow, I've got the perfect opportunity to make a six-membered ring, up, down, out, and that will make me a six-membered ring. 1, 2, 3, 4, 5, 6. On carbon 2 is my carbonyl. 3 is a CH2, 4 is a CH2, 5 is a CH2, 6 is my other carbonyl. Another Claisen product. This is going to be the final product of this reaction. So beware, beware of looking at all the possible pathways and ending up at the most stable product you can have. Synthesis-wise, I'm not going to go through this problem. It would take too much time, but we can go through it in class, or I can make another mini lecture. But the screaming bell and whistle, as you see, is that I've got the 1,3-dicarbonyl, so this should make you think, I got to make this guy out of a Claisen. So it could possibly be made from this carboxylic acid derivative and this enolate. Or it could be made from this enolate and this carboxylic acid derivative. Make sure you look at those and see that both of those are equally valid ways to get to that product. But in the meantime, I hate to bring this to a close, but I will close it off with such a fantastic joke. A man walks into a bar and orders a beer. It's always a man walks into a bar. A woman walks into a bar and orders a beer. The bartender serves the drink and says that'll be $5. And this is definitely a kind of a pricey bar. This is not a bar in Morris. So the woman opens her wallet and places a $20 bill on the bar. Sorry, ma'am, the bartender says, but I can't accept that. So the woman grudgingly pulls out a $10 bill and places it on the bar, and the bartender, shakes his head again and says, no, can't accept that either. So the woman's like, what's your problem? My money's perfectly good. What's going on? And then the bartender simply points to the sign above the door and explains, ma'am, this is a singles bar. Yeah, okay. We'll talk about the Claisen class. Bye.